In number 5, this is a review question about drawing a mechanism for a Grignard reaction. And if you recall, a Grignard reaction is nucleophilic. Where the ethyl group that's attached to the magnesium bromide is our nucleophile. And the carbonyl carbon is the electrophile. So this is going to attack here. That ethyl group is added, and the oxygen can't come back down because there's no leaving groups here, so it'll just pick up a proton from water. So we do a proton transfer there. And that's the mechanism for that one. Here we're drawing a mechanism for the formation of an acetal. And the first step is a proton transfer with that catalytic acid. So our electrophile is much better now because it's been activated. We have excess methanol, which is going to be our nucleophile. So the oxygen lone pair electrons can attack here. And everything on the methanol comes along, including that hydrogen. So this is positively charged. These reactions are reversible. So what we're going to do here is, the goal is to kick off that alcohol group as water. So we're going to do a proton transfer. So that hydrogen will jump over to the other side. The lone pair electrons from the oxygen here is going to come down to reform that double bond, kicking off water. So in that step we lost water. So we have this new electrophile and the OMe, where the oxygen is positively charged. Now a second molecule of methanol can come in and attack. That hydrogen is still there, and that can just get picked up in a proton transfer to give us that product there. And to do a deprotection of the acetal, all of these arrows can be pushed in the backwards direction, and you would get to the starting carbonyl. All right, in number 8, we're looking at proposing a synthesis. And you might look and see that all that we're doing is adding a carbon, so you may be inclined to just add NaNH2 and CH3Br. However, if you recall, the proton, or the pKa of the proton here, is around 25. And the pKa of this proton is around 20. So if we added NaNH2, that proton over there is going to get picked up first. So we're not going to have the desired synthesis there. So that one's not going to work. The way to make this work is to disguise that carbonyl, and we can do that by using an acetal. And to add an acetal, you just need catalytic acid and an alcohol of your choice. So you can use ethanol. So that will add 2 ethoxy groups onto there. My alkyne is still here. Now I can do the NaNH2 and CH3Br. and then we've added that extra carbon. And to get back to the carbonyl, you just use acid and water. The next problem is similar, except if we wanted to do the synthesis here by adding two phenyl groups, that's often done with a Grignard reagent to an ester. And we also know that Grignard reagents can react with carbonyls or ketones, so we want to protect that or disguise it. So again, you can use catalytic acid with an alcohol. So I'm going to use this alcohol, which will make this cyclic acetal. You could use ethoxy or methanol if you want. And then once we have the ester there and the ketone being protected, we can add phenyl magnesium bromide, excess, followed by acid. So usually we do Grignard, then we follow the second step with water, but if we add acid plus water, that will deprotect that acetal in the process. We form the alcohol and add the two Grignards. All right, here is another mechanism question. This is similar as forming the acetal. Here we're going to form a hemiacetal. The same first step is there, the proton transfer. So now we have that good electrophile. And instead of an external alcohol attacking, we have an alcohol within the molecule. This is going to be an intramolecular reaction. And that alcohol is going to attack the carbonyl, and those electrons will go up. So we're forming a new bond here. And I had 1, 2, 3 carbons to that oxygen. So I'm going to flip one of these up here. And so that's not the prettiest structure. Actually, I might be missing a carbon. 1, 2. All right, so that's not super pretty. But we have the right number of carbons there. And the alcohol hydrogen is still here. And we can just do a proton transfer. And then you can redraw that one. So starting with cyclopentanone. And we can use any other reagents. There's no limitations on carbons. So I noticed that I need to add a carbon and do an elimination. So to add a carbon, I'm going to use a Grignard, followed by water. I'll get an OH and the methyl group here. And if I convert that alcohol to a bromine, I can then do an elimination. And I'm going to use a small base like DBU or sodium hydride in order to do that elimination. If I use T-butoxide, then I'll eliminate to the outside, and I don't want to do that. Again, we're going to start with cyclopentanone. So I have an alcohol and an extra carbon. Alright, so I can do, let's see, this one is the halonitrile, or the cyanohydrin. So we can add the OH and a nitrile, and then if we react this with acid and water, that will hydrolyze that nitrile to the carboxylic acid. Alright, here, cyclopentanone. Okay, the only thing I did here was add an oxygen, so I went from having a ketone, or a cyclic ketone, to having a cyclic ester, or a lactone. And a reaction that we know that does that is MCPBA, or the Baeyer-Villiger, which will add an oxygen in there. So the number of carbons is the same there. Okay, here we have a carbonyl and a secondary amine. The first thing that will happen is we'll form the imine, and that's going to be positively charged, and then you have water so that we can form the enamine. In this problem here, we're looking at the products from what is expected for acid conditions with an imine. And this one will just go back to the carbonyl, so you can think of slicing it there. So we get a carbonyl plus NHCH3, or NH2CH3. So this is an enamine. So we can imagine that there was a double bond here before. With the two methyl groups, which would have come from the carbonyl there. Should have that beautiful looking carbonyl. Plus dimethylamine, or you can draw it flat here. So either of those would work. Alright, major products here. We have a ketone with sodium borohydride, which we've seen in chapter 13. This is going to reduce our carbonyl to an alcohol, and everything else will be left alone. Here we're reacting a Grignard with a carbonyl. So that's going to get converted to the alcohol when we add acid. We have that methyl group, and then we're going to add a phenyl group here. And the other thing that acid does is it will deprotect this acetal to give us the ketone back. Right, here is a synthesis reaction, or just a short one. In the product here, we're adding a carbon, and that's the only thing that is different. In a reaction that we know how to add carbon is Grignard. And if we add it to a carbonyl, that will give us an alcohol. So what we need to do is make this carbonyl. And I just want the aldehyde, so I'm going to use PCC to give me the aldehyde. Then I can use methyl magnesium bromide, followed by water. This is a Wittig, so you can imagine putting this on top of where that is. So just draw your ketone, the double bond, and then you're just going to plop everything over there. So 1, 2, 3 carbons. This first one is number 1, 2, 3. Here we're doing a synthesis. A couple of things that I'm observing is I have 2 carbons. So I'm adding a C and O. And my triple bond is gone. So if I try to add a carbon to the end of the triple bond, that would give me the carbon in the wrong position. I need it at the 1 position. What I can do instead is make a Grignard at this position and attack formaldehyde. So I could have this Grignard plus formaldehyde. So in order to make that Grignard, there's a couple of things that you can do. You can reduce the alkyne to the double bond and then add HBr. So this would be Lindlar's. Then add magnesium. That will get your product. You can also just reduce it all the way. Do MBS. And then you could proceed from there. And I think that's most of the options there. There could be others that you could come up with, probably. Those are the 2 that came off of my head there. All right, here is another synthesis. Okay, so for this reaction, I noticed that I have a ring opening and also that I've added carbons. 2 carbons. Where there's also an OH. So that might be from a Grignard. These 2 right here. And that might be a Grignard to an ester. So I need to make an ester or a cyclic ester out of my ring. So what I'm going to do first is make a functional group handle. So if you were going to do a retro here, would look something like that. All right, something like that. So that's what we're aiming for. And so once we do this Br, we can use sodium hydride to make an internal alkene. Then I want to form an alcohol on the less substituted carbon, so I'm going to use BH3. And peroxide. Then we can oxidize that. And then to make that lactone, or that cyclic ester, we can use MCPBA to do the Baeyer-Villiger. And the tertiary carbon will shift before the other ones do. And then we can react it with excess methyl magnesium bromide, followed by water. All right, here we're going to predict major products. When things are reacted with acetone. Acetone is the same thing as 2-propanone. So for A, if I react acetone with with ammonia, that will give us this imine. Just NH. If you react it with a a primary amine, you'll still get an imine, but it will be at the N plus whatever R group's on there. For C, we react it with excess ethanol. We're going to form an acetal. D, we have a secondary amine, which will first form the imine or iminium, but then that will tautomerize to the enamine. For E, we'll get that. And then for F, we get the oxime. Same thing here, acetone. G will reduce it to the alcohol. H is the Baeyer-Villiger. I will form the cyanohydrin. J will add an ethyl group. K is the Wittig. So I'm adding 1, 2, 3 carbons. 1, 2, 3. And lithium aluminum hydride will reduce to the alcohol. All right, to make this enamine, we can imagine the iminium that was here. And then we can cut that in half. We end up with cyclopentanone. Plus that compound. So these two things plus catalytic acid will get you that enamine. All right, mechanism here. First step, proton transfer. Water can attack. So in the first thing that happens with these weird enamines, the electron lone pair from the nitrogen will actually come down here to reform that double bond. And one of those pi electrons can grab water, or a proton from water. So we have this iminium. and the hydrogen that it has added here. And now we have this carbon double bond nitrogen that looks like a carbonyl. So this can attack here. And nitrogen gets its lone pair back. We're going to do a proton transfer. And the electrons from the oxygen can come in to form this double bond, and then we're going to break that bond there. And that is the product. Oops, nope. There's a hydrogen here, and then it's just a proton transfer. All right, here is another synthesis problem. We're adding a whole bunch of carbons here. 3 C's and an alkene. So this makes me think of a Wittig reaction. If I just do the cleave here, that would be this plus that reagent. So I need to make cyclohexanone from cyclohexene. I can do acid and water to get the alcohol. Oxidize to PCC, or with PCC to get the ketone, and then we can just add the Grignard reagent. And that's 3 carbons that are added there. Here is another one. So if I look at this retrosynthesis here, that is an acetal. I have 2 oxygen groups on the same carbon. So this would look like that. So I need to make this carbonyl from these 2 bromines. This makes me think, those 2 bromines that are on the same carbon make me think of this, which I can make from that dihalogen here. So I'm going to use excess NaNH2 followed by water to do that double elimination. And then use H2SO4 with mercury sulfate and water. That will give me the ketone. And then to get to here, I just use excess methanol plus acid. In this one, I can recognize that I have an acetal right here. So there's 1 carbon with 2 O's attached. And this makes me think of a diol, where there's 2 alcohols that can attach to this formaldehyde. And so those 2 alcohols can form the acetal on that formaldehyde. And to make that diol, we can use KMNO4. That will give me the syndiol, and then I can just add that and formaldehyde with catalytic acid. Alright, this one here is another acetal. That came from here. which might come from the alcohol before that. And that from there an alkene. Which I can get to eventually from this starting material. So I have no functional groups here, so I need to put one in. I use Br2 and light. And I want to make the external or less substituted alkene. So I'm going to use T-butoxide here. And then I want the alcohol on the less substituted position, so I use BH3. Oxidize. And then the alcohol used here has 2 carbons and it's a diol plus catalytic acid. Now here we're looking at a cyanohydrin, which came from a carbonyl plus the HCN, or NaCN, or KCN. So I need to put an alcohol there. Oxidize that. You can use KMnO4 or a milder reagent like PCC or DMP or SWERN. And then to get this, you would use the KCN or NaCN, HCN.